Imagine an observer positioned on an exoplanetary surface, many light-years distant, gazing upon the night sky. Amidst the celestial expanse, three luminous sentinels command attention, aligned in near-perfect formation. This configuration has transcended generations, serving as a navigational guide for ancient mariners and a foundational reference for astronomers. Today we embark on a comprehensive exploration of Orion's Belt, a remarkable asterism that encapsulates fundamental astrophysical processes and profound cosmic evolution. Orion's Belt constitutes a prominent asterism within the Orion constellation, composed of three high-mass blue supergiant stars, Alnitak, Alnilam, and Mintaka. These stars, although appearing relatively proximate from our terrestrial perspective, reside at varying distances and exhibit distinct astrophysical characteristics. Alnitak, Zeta Orionis, the southeasternmost star, is a hierarchical binary system dominated by a massive O-type primary component approximately 1,260 light-years away. This star radiates at an extreme surface temperature exceeding 30,000 Kelvin, with a bolometric luminosity surpassing 250,000 times that of the Sun. Alnilam, Epsilon Orionis, centrally positioned, is the most distant and luminous of the trio, located roughly 2,000 light-years away. Classified as a B-type supergiant, its intense stellar winds sculpt the surrounding interstellar medium, actively contributing to the evolution of nearby nebular structures. Mintaka, also known as Delta Orionis, is the northwesternmost star in Orion's Belt. It's a complex multiple-star system with at least two gravitationally bound components. These stellar constituents execute a mutual orbit within a period of several days, exhibiting intricate dynamical interactions characteristic of close binary systems. This alignment, while appearing serendipitous from an Earth-based vantage point, is a consequence of our specific orientation within the Milky Way rather than an intrinsic astrophysical correlation among these stars. Their immense size and radiative output place them among the most transient and influential stellar entities within our galactic neighborhood. The origins of Orion's Belt are deeply intertwined with the expansive Orion Molecular Cloud Complex, an extensive stellar nursery comprising vast reservoirs of molecular hydrogen and interstellar dust. This region represents one of the most active sites of high-mass star formation within the Milky Way, spanning over 500 light-years and hosting multiple H2 regions, including the renowned Orion Nebula. These massive stars underwent gravitational collapse within dense protostellar cores approximately 6 to 10 million years ago, catalyzed by instabilities within the surrounding molecular medium. Their rapid ignition of nuclear fusion led to their classification as high-mass, short-lived stars. Unlike G-type main-sequence stars such as the Sun, which persist for billions of years, these supergiants are destined for catastrophic core collapse supernovae within mere millions of years. At present, the intense ultraviolet radiation and stellar winds emitted by these behemoths are actively dispersing the residual nebular material, shaping intricate shock fronts and ionization fronts observable in high-resolution astronomical imagery. The intricate interplay of radiation pressure, magnetohydrodynamic forces, and gravitational interactions within this environment continues to fuel ongoing star formation. If you are enjoying this video, then why not subscribe to the channel? Approaching Alnitak, we would be confronted with a formidable stellar environment, one where the extreme radiative flux dominates the local interstellar medium. The presence of its binary companion induces gravitational perturbations, affecting mass transfer processes and stellar evolution. Alnitak's association with the Flame Nebula, also known as NGC 2024, and the Horsehead Nebula, Barnard 33, highlights its profound impact on the morphology of adjacent dust clouds. As we traverse interstellar space toward Alnilam, we would observe its luminosity permeating vast expanses of surrounding space, significantly influencing the nearby reflection nebulae. The sheer mass loss rate of this supergiant, estimated at millions of solar masses per million years, further accentuates its pivotal role in reshaping the stellar cradle from which it emerged. Mintaka, in contrast, presents a dynamically intriguing environment due to its binary configuration. The mutual orbital interaction between its components induces periodic variability in brightness, detectable through high-precision photometric measurements. The presence of an extensive stellar wind interaction zone between its constituents provides a unique case study in mass exchange within massive binary systems. Throughout recorded history, Orion's belt has served as a cornerstone of celestial navigation, mythological interpretation, and architectural alignment. The ancient Egyptians meticulously aligned the Great Pyramids of Giza with Orion's belt, positing that these structures facilitated the ascension of pharaohs into the afterlife. The Mayan civilization integrated Orion into its cosmological framework, incorporating it into astrological and agricultural cycles. Indigenous cultures spanning various continents utilized Orion's belt as a fundamental navigational reference, predating the advent of modern celestial cartography. From an anthropological standpoint, the recurrent association of Orion's belt with hunting deities, warrior archetypes, and celestial pathways underscores its profound psychological and cultural significance across disparate civilizations. Betelgeuse, a highly evolved red supergiant, resides within the Orion constellation and is currently approaching the terminal phase of its stellar evolution. Situated approximately 640 light-years away, this M-type supergiant exhibits erratic luminosity fluctuations, indicative of convective instability and advanced nuclear fusion processes. In recent years, Betelgeuse has undergone anomalous dimming events, suggesting either extensive dust ejection or pre-supernova structural perturbations. Imminent core collapse. The depletion of silicon in Betelgeuse's core will precipitate the onset of iron core formation, an irreversible precursor to core collapse and Type II supernova detonation. Observable consequences. Upon undergoing supernova, Betelgeuse is expected to emit a transient outburst exceeding the luminosity of the full moon, persisting for several weeks before gradually fading into a remnant neutron star or black hole. As we return from this theoretical voyage, we are reminded of the dynamic, ever-evolving nature of the cosmos. Orion's belt, far from a static celestial ornament, embodies the perpetual cycles of stellar birth, transformation, and demise. If you liked this video, then why not like, subscribe and leave a comment.